Okay, just waiting for it to roll. Good afternoon, everybody. My name is Saleh Alazemi, consultant respirologist from Amiri Hospital. I'm glad to share some of the clinical aspects of COVID-19 disease. So just waiting for the slide to go through. Okay, so after all, COVID-19, it's a viral illness, it's a bad flu. So I guess to understand it, we have to speak its language. So basic virology is very important. We are all aware of the coronaviruses. It's a family of hundreds of viruses circulating in the animals and humans. We encounter them regularly on a seasonal basis, like as a common cold. However, 3 of them are known to directly invade the lung in humans and cause pneumonia and deaths. Those are MERS, SARS, and SARS COVID-2. Those viruses, if you look at the picture, they are characterized by the spike protein, which gives them their name, the crown viruses. Those spike protein are very important, and they are the most elite or well-known protein of those viruses, although there are other protein there. The S protein or the spike protein are the main target for our vaccination, and also they are the one that get attached to their target receptor and the host cell. The viral cycle or life cycle in the host cell actually can break it into 4 phases: attachment to ACE2 receptor, cell entry through endocytosis and uncoating. The 3rd stage is biosynthesis, where the virus replicates itself using the cell own machinery. And finally, it will exit the cell and go to infect other cells. We can draw several clinical implications from this basic science. First, let's talk about the ACE2 receptor. We know that ACE2 receptor is actually very well expressed abundantly in the respiratory symptom GI and endothelium. That can explain the tendency of this virus to cause severe pneumonia, GI symptoms, and vascular thrombosis. The second thing, we also know that ACE2 receptor is only expressed in human, fully expressed, after the age of 20. So that's why you don't see this disease frequently in kids and teenagers. And whenever they get it, they usually get the mild form. Another implication from this, also you can see each of our therapies, they target special step on the virus cycle. For example, we all remember the chloroquine, where we used it very frequently early in the disease. Of course, it doesn't work right now, but at that time, everybody was crying out loud to use it early in the disease, even as a prophylaxis, because it acts early in the first step, viral entry. Whereas Kaletra, remdesivir, and other medication, actually, they act later on. That's why we use them when the patient gets sick in the later stage of the disease. So we also cannot blame all the damage to the virus. Our own body, our own inflammatory system actually causes the most severe form of the damage. If you break down the disease spectrum of COVID-19, you start with a viral response in the early stage. You'll get the usual viral symptoms, the fatigue, dry cough, fever, malaise, and that's usually due to the viral replication and the viremia happening in the blood. The second stage, most of the patient actually, they will recover here, but some of them, they will progress to the second stage, what we call the pulmonary phase, where it's an interaction between direct viral damage to the lung and also a host inflammatory response. And this phase is mainly characterized by shortness of breath, hypoxemia, and chest infiltrate on imaging. The majority will recover as well. However, the unlucky minority, they will progress to the 3rd phase, what we call it hyperinflammation phase, which is characterized by intense inflammatory response with ARDS, shock, and multi-organ system failure. So if you compare this virus to its cousins, SARS and MERS, it doesn't look that bad. Actually, it's the nicest out of them, where MERS kills 34%, SARS killed around 10%. This one is around 2 to 3% the mortality rate. But what is peculiar about this virus is the speed and efficacy of spread. For MERS, it took the virus around 1,000 days or 2.5 years to reach the first 1,000 case. For SARS, it took it around 130 days. For this our new friend or a new enemy, whatever we call it, it only took it a month and a half to reach the 1,000 landmark. And from there, it's kept soaring, spreading the whole globe, sparing no country, resulting in the worst pandemic that we've seen in decades. Currently, we're almost around 18 million globally, with around 700,000 deaths. As you can see, the hotspot or the epicenter right now is the Americas, the United States, Brazil, and also the South Africa is coming up on the 3rd or 4th place. In Kuwait, we're almost reaching the 70,000 total cases. The good thing is the mortality rate is still below the 500, which gives you a mortality rate less than 1%, which is good. Now, that's total. If you look at the trend, we can notice a small trend toward lower daily cases. Our current R0 is around 1.04. However, that might be due to different policies for testing and examining different patients. But what is a solid outcome is the daily death, which is surely coming down, which is a good thing. So what makes this virus so dangerous? How does it spread this fast? Actually, it all comes to two things: the pre-symptomatic and asymptomatic spread, and the high viral replication in the upper airways. This is very peculiar for this virus. Comparing it to the pandemic flu and SARS COVID-2, if you look at the last row, those viruses usually they reach their maximum infectivity and highest or peak viral load in the upper airways several days after the onset of symptoms. So the policy of test, isolate, and quarantine works very well for those viruses. However, with SARS-CoV-2, if you look at 0, by the time the patient comes to you with symptoms, he's already maximally infective, and he already reached his peak viral load. So by the time he comes to you, he already infected several people. So it's very hard to contain this virus. Also remember, this is a global problem. The virus has a global impact. Not only it has a social, economical, and political impact. So whenever you read new guidelines or rules or whatever, you have to keep in mind that the policy making are taken into account all those factors to make this guideline. So you always have to tailor it according to your own country, region, and institute. How does it transmit? Still, the majority of transmission happens through close contact, through respiratory droplets. Keep your distance and wear a mask. When the infected patient breathes, the large respiratory droplet usually fall on the ground because of the gravity within 2 meters. So keep the distance and wear a mask. Other possible route, of course, contaminated surface, fecal-oral has been mentioned, and there been confusion about the aerosolization, which is the airborne route of transmission. It's not yet confirmed, but it's definitely a way of transmission under special circumstances, like when you are performing the AGP, aerosol generating procedure, like intubation, bronchoscopy, and etc. So in this condition, you should take extra precaution. Another thing you have also to mention is the infectious dose, which means how many viral particles you need to inhale to establish an infection. And from estimated guess extrapolating data from other viruses, it's around 1,000 viral particles. You can take them all in one breath, 10 and 110 or 10 and 100, whatever. But once you reach 100 viral particles in your body, you are likely to get infection. And here you can see the difference between the different activity where if you are facing a patient. Breathing, usually it's not that bad, breathing and speaking, but the worst thing if the patient is coughing or sneezing, because they can produce over 200 million viral particles at high speed. So those are the activities you have to be aware of. Once infected, usually the incubation period is around 5.3 days, ranging from 2 to 12. What does that mean? That means is those who are infected by day 14 here, 99% of them, they will develop symptoms. And actually, this is the basics behind the recommended quarantine period of 2 weeks. Initial presentation, nothing pathognomonic, nothing rules it in, nothing rules it out. It's a viral illness and it can present in a variety of ways. So don't pay or put a lot of weight on the clinical presentation. One thing we have to keep in mind, we always, early literature from China said that 90% they have fever. And if you see in the airport and the hospital, they scan the people with the temperature scan to see if they are afebrile, they let them in. The absence of fever at presentation does not mean anything. Actually, less than 50% of COVID-19 patients, they present with fever. But the majority of them, they will develop fever along the course of their disease. We already talked about that, the different stages of the disease. So we'll move to the diagnosis. So living in this era of medicine in a country with the easy access to a lot of diagnostic can be a blessing. However, if you don't know what to order and what to do with the result, or like what you call it, it's in the wrong hand, those tests can yield more confusion than clarity. So you have to know exactly what you are doing. So starting, if the patient has contact with a positive case, the first step you want to establish is the patient got infected or not. So you want to diagnose acute SARS COVID-2 infection. And there is only one way to do that. It's the molecular testing, or what you call it, nucleic acid amplification test, which is also known as a PCR. That's the only way. This is a gold standard, and there is no other way to diagnose acute SARS COVID-2 infection. Antigen detection actually is a promising technique, and it's been used in some places, but it's not widely available commercially right now. So after you diagnose an infection, the next step you want to decide, okay, some of the patients, they will remain asymptomatic, and some of them, they will express the phenotype of overt COVID-19 disease. Here comes our clinical, laboratory, and imaging data. Why? Because that will help you to determine, to stratify the patient, the severity of the disease. It will help you to predict the prognosis, because only with that you can triage the patient, whether to send him home for a mild disease, keep him in the ward, or admit him to the ICU. And also based on that as well, you will formulate a proper treatment plan and follow-up. Another important and very critical importance of those data, the clinical, lab, and imaging, is to formulate your pre-test probability. You never read a PCR result alone. You always combine it with a pre-test probability to end up with a post-test result. Finally, the patient either recover or die, and for those who recover, the serology testing actually comes in place. Currently, antibody testing is only indicated for epidemiological surveillance. You want to know how many of your population gets infected and what's the general situation in the country. They are not indicated for the diagnosis of acute infection. So the right test, do the right test for the right purpose, but also timing is of an essence. You have to know when to do it. You have a very limited windows for each test. Early on the disease, you have your PCR windows. Later on, you have to change the type of samples from the nasopharynx. You go down to the alveolar. Later on, the only way to do it is through the serology. Also, the viral load in different samples differs according to the samples and to the disease severity. Patients with severe disease, they tend to shed the virus in their airways for a longer period of time. On the right side here, you can see the endotracheal aspirate, which is samples from the lower respiratory tract infection. They tend to remain positive for a longer period of time than the saliva or the nasopharyngeal swab. So you need to know your timing of the test. I'm not going to go through the details of the PCR, but I highly recommend you to review your basic micro and PCR technology, because you'll come across it very frequently, especially with every single publication. You need to know what they're talking about, like the cycle threshold, limited detection, so on and so forth. But what you need to know is that there is no single test that is 100% accurate all the time. Each test has its own flaws, and PCR is no exception. When you're talking about the limitation of the PCR performance, sorry for the type of here, it's PCR, we can divide them into pre-analytical and analytical error. Analytical refers to the kit itself, the test itself. There is a flaws or a malfunction in the test. But the most important thing here is the pre-analytical error. First, the type of swab. Not all swabs yield the same results. You have the nasopharyngeal, oropharyngeal, nasal, and the anterior middle turbinate. The best for SARS CoV-2 is the nasopharyngeal, because we know that this is the place where the viral replication is maximum. Another errors might arise from the technique of the collecting the swab, the type of swab. Each swab serves different purpose, and also storage and transportation. We already mentioned the type of samples, the different type of samples. Usually the BAL has the high sensitivity. Next is the sputum and the nasopharyngeal swabs. Usually the sensitivity of nasopharyngeal swab PCR around 70%. Analytical error, what do we mean by that? That means what's the type of PCR machine are you using? Is it validated or not? What type of probe and prime they're using? How did they validate it? Last time I checked the FDA page, actually that's 2 weeks ago, they already have, you see here, almost 100 available PCR tests just approved by the FDA. Remember, none of them has been approved according to the formal channel of the FDA. All of them had received EUA authorization. That means emergency use authorization. If you are wondering what does that mean, that means you can submit your test with a very minimal data, as small as 30% or 50%, and you get approved. So you have to be careful, and you have to know your kit. Finally, PCR interpretation, positive, negative, equivocal. What do we mean by equivocal test? So in general, we test 2 viral genes and 1 human control. Proper PCR test, the human control should be positive. That tells you the kit is working. And then the 2 viral genes that you choose, they have to be positive. So if they're all positive, the test is reported positive. If the human control is positive, the viral genes are negative, this is reported as negative. Any other combination will be reported as equivocal. And remember, equivocal should be dealt with as a positive until you repeat the test. So how can you minimize the diagnostic errors of SARS CoV-2 test? I think the single most important is to use your pre-test probability. What do you mean by that? Pre-test depends on the prevalence, exposure, clinical data, and the timing. If you look at this graph, this is the green line is actually for a test with a sensitivity of 90%. Forget about that, because our test PCR is 70%. So let's focus on the blue line. So you have to formulate your pre-test probability. For example, let's imagine an ER doctor comes to you with a fever, shortness of breath, and chest infiltrate after being exposed to a COVID-19. So this is a high pre-test probability, above 70, let's say 70. So if you have a PCR negative, which is the blue here, the post-test probability of the disease is still 40%. So your test result doesn't mean anything. So that's why you have to combine the two data together to arrive at the best decision. So, closing remark, I would like to just close by a few remarks. I think our understanding of COVID-19 is still evolving. We should be prepared to change our views according to the available evidence, and the evidence are being changed on a weekly basis. COVID-19 disease, I think it's here to stay. I don't think it's going anywhere in the near future. So we have to observe your diligence, wear a mask, watch your distance, and wash your hand. And finally, use your available diagnostic wisely. Thank you, everybody, for listening. Dr. Wael, the mic is yours.